Hello, 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 hello.
फिर आए मैंने बुला नहीं था उन लोग को भी बुलाइए गुप्ता सर स्टार्ट
अभी कर दे।
स्टार्ट कीजिए टाइम बोला गया सर
Good afternoon, everyone. Uh,
इसको पकड़िए तो कल घुमाएंगे
it is my it is my pleasure to introduce Dr. Kamlesh Jana, University of Ottawa, USA. Dr. Jana is a dedicated academician and a research actively engaged in teaching and research in his field. Though his scholarly work, publications, and participation in national and international conferences, he has been contributing significantly to the advancement of scientific knowledge and higher education. We are delighted to have Dr. Jana sir with us today and look forward to gaining valuable insights from his expertise and research experience. Jana sir.
कमल सर यू कैन स्टार्ट सर यू कैन स्टार्ट सर
Okay. So yeah, I'll share my screen. Okay, 1 minute. Is my screen? Can you see my screen presentation? Hello.
हाँ यस यस वी आर हाँ यस यस यू कैन ऑडिबल सर यू कैन
Proceed.
सर यू कैन प्रोसीड
So is my slide changing?
या स्लाइड इज हाँ 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 स्लाइड इज विजिबल स्लाइड इज मूविंग
Hello.
slide is visible and moving
Okay. Then I'll start. Okay.
thank you
Okay. Okay. Yeah. So thank you everyone, and I'd like to thank first the organizing committee for inviting me to this seminar. So today I'll talk about light-induced ultrafast current in material. Mainly I'll talk about in solid and their how actually control those current and what are the application those ultrafast current has. So this is the brief outline of the plan of my talk. So first I'll give a brief introduction and the motivation behind this project. Then I'll talk about how we currently using the light field, we control such current using structural light field, and how we generate programmable current and we detect such current. And in the next part of my talk, I'll talk about terahertz electromagnetic radiation that is radiated from such dynamic current. And mainly there I'll talk about a special type of terahertz mode. We call it a flying donut terahertz mode, and the current control in other type of like low dimensional material, and then I summarize. So the ultra fast current or the current generation control in ultra fast time scale has many potential applications like exciting terahertz field or ultra fast electronics, ultra fast switching, or in solar cell material efficiency measurement or material probing. But among those applications in my today's talk, I will mainly focus on this magnetic field pulse or terahertz bandwidth magnetic pulse excitation and terahertz radiation from such current. Now the If I say the terahertz technologies, and if I just introduce what is terahertz is nothing but this is the part of the electromagnetic spectrum we have, and it resides in between microwave and infrared. And in terms of frequency, it starts from 0.1 terahertz to 10 terahertz. Conventionally, this is called the terahertz range. And in terms of wavelength, it comes from 30 micron to 3 millimeter. And this terahertz is very, very interesting, and this very, very useful. It has many applications, starting from next generation communication, like we have now 5G, probably 6G and beyond 6G. So this frequency range will be used, and also in sensing and imaging. It has many, many applications. Now, first, as I told, today I'll talk about mainly the very short magnetic field pulse generation from such current and terahertz radiation. So I'll start with what was the primary motivation behind this project or the research. The primary motivation was to generate very short magnetic field pulses. So the mainly magnetic field we see or we use in daily life or in many research lab are all the electromagnet. When we send current through the wire, superconducting or conducting wire, magnetic field will be generated. But this kind of magnetic field has some like limitation, like we cannot generate really short pulses. That's why it's very difficult to do some pump probe kind of experiment. It's not easy to synchronize with the diagnostic method we have. And also spatial arrangement using this wire-based magnetic field is problematic. So basically there is no easily accessible method that can generate very short and very strong magnetic field. There some research has been done, but that was done at let's say very large accelerator facility like Stanford Linear Accelerator. There, if you focus very high energetic electron beam, you can generate such field. But as I told, you have to this very, very inefficient process, because you need access to really large accelerator facility to this kind of experiment or to have this kind of magnetic field. Now, what is the alternate route? So what alternate route we are suggesting that nowadays femtosecond laser or ultra fast laser is available in many university laboratory. So these femtosecond pulses can be used to generate and control current in solid or gas and material, and such current will be the source of a magnetic field. So a few years back, theoretically, it was shown that using special type of 2 femtosecond laser pulses, it's possible just like create a solenoid ring current. So here in this picture, the left side, you can see this just like a ring current. And as there is a ring current, according to electromagnetism, so there will be magnetic field at the center. So this is the very strong magnetic field at the center of the ring. And also as this is generated by very short current pulses, so the magnetic field will be really, really fast. Like it has femtosecond rise time, and also it will be isolated, spatially isolated, as it resides at the center. Now, to generate such short pulses, how do we generate current? There are many techniques we can generate, but one of the effective technique that we took, that we call the two-color coherent control or coherent control. Here, using the waveform of the light pulse, we generate and control the current. We use a two light pulse, one at frequency, angular frequency omega, another is just second harmonic of that, and we mix that. Using the relative phase between them, we can control the direction as well as the amount of current we inject or generate. And only by changing the relative phase, we can control the direction and amplitude. That's why when you're changing the relative phase in this picture, you can see this is oscillating sinusoidally. So that means we're changing the amplitude as well as the direction. Now here, how do we understand the current generation using this method mainly in solid or the semiconductor? So this can be understood by quantum interference process. When you're applying two pulses, and one pulse photon energy is above band gap compared to the material we are applying, and another is below band gap. So we are exciting two processes. One is called the single photon absorption process, another is two photon. As there is two quantum pathway, so there will be quantum interference, and due to this interference, so at the conduction band, there will be asymmetry in the momentum space of the electron distribution. So this asymmetry in the momentum space, that leads to the generation of the current, and such current amplitude depends on the electric field we applied of omega field and 2 omega field, as well as the relative phase. So that's why it is a sign of delta phi. So delta phi is relative phase. That's why you can see when you're changing this delta phi, the current is oscillating sinusoidally. And now the mainly the light mode or the laser mode we use, these are generally conventional Gaussian beam, especially Gaussian beam like this on the left side, so that the generated current, if we apply such field, will be almost unidirectional. The current direction will be same across the beam. But nowadays there is a lot of specially structured beam available. If we use such beam in this experiment, how the current will behave? So that was answered a few years back, where we applied two azimuthally polarized pulse, and it was shown that when you apply two azimuthally like such donut beam, then the current also become like a donut or the solenoid current, and the magnetic field was calculated. But this was really nice demonstration. But one problem was that every time to generate such pattern in the experimental setup, you have to change the optical element to generate different type of current distribution. So clearly we cannot reconfigure the current we want to generate. Every time you have to change the optical element and you have to generate different distribution. So this was the limitation. Next we thought, what if we try to generate a reconfigurable current? Now, without changing any optics, we will just do something to the light, so that will generate different type of current distribution, the current pattern. For this study, what we did, we used a circularly polarized fundamental beam and linearly polarized 2 omega or the second harmonic, and this gives us fully directional control of the current they generate. And here we use the special light modulator, and I'll come to this picture, it will be easier to explain. So this was the experimental setup. So you can see this is the main beam that is coming, and its central wavelength is 1.5 micron. Then there is a crystal that is generating 2 omega, and then this is just an interferometer which is separating the two beam, and we are combining at the end, say 1.5, and its second harmonic is the 740 nanometer or 750 nanometer. And here one of the element I called, this is a SLM. So SLM is nothing but all of you know the LCD TV is just like LCD screen. So it has many pixel, and at each pixel, by applying an appropriate voltage, I can control the phase or the phase front of this beam which is reflecting from it. And for our case, we are reflecting linearly polarized omega beam. So at each pixel, we can control the phase, what will be the phase front of this pulse. So that means we are doing same thing like this coherent control, two color coherent control. But as we have many pixel, we are doing just this in pixelated manner, by pixel manner. Or you can say this is just spatially resolved coherent control. So it has many pixel, and each pixel we can decide what will be the relative phase between two beam. And at the end, there is a homemade current detector we used. This is just a 25 micron single pixel detector based on low temperature gallium arsenide, and we just raster scan this detector across the two beam profile to measure the spatial distribution of the current. And this was the detector architecture. So you can see these are two aluminum electrode on top of this gallium arsenide, and we put a mask, and you can give it just give us the single square pixel detector. And the characteristic of this detector is that this direction sensitive, it depends on the polarization direction of the light. So, and only we can measure one component, X or Y component once, then we have to rotate it by 90 degree to measure the other component. So first what we did, we just kept our detector fixed, and we just measured the X and Y component of the current. So this is the measure result. So you can see that this is the two current when we are changing the relative phase, and they are oscillating pi by 2 out of phase. Now if we just parametrically plot this experimental data, so you get almost a nice circle. So this tells us that only by changing the relative phase, we can now like rotate the current in any direction from 0 to 360 degree. So this is the case for a single current element we are talking about. Now, this is the building block or the basis of a reconfigurable current pattern of the reconfigurable current circuit, because using this technique, we can excite hundreds and thousands of such small or tiny current element, and we can now control the direction and amplitude of each current element. And we can rotate this current element in any direction, like 0 to 360 degree, only controlling the phase. So to apply this technique, what we first demonstrate that, we demonstrate a optoelectronic interconnect. So here, the top of this slide, this is the target circuit we would like to excite. So you can think of there is a left side, there is an imaginary electrode, and right side there is three imaginary electrode, and this left and right can be connected by three different way like this. Now we would like to excite similar thing only by controlling the light's properties. So this is the kind of SLM phase we apply to the computer or to the SLM. And here the bottom panel, this is the measure current you can see. And here you can see the current is almost like following like what we would like to excite like a target circuit. But one thing is interesting is that so there is no predefined circuit or no wire, nothing. So this is just a plain semiconductor. There is no structure, nothing. And what we are just exposing is to light pulses, and by this we can generating almost wire-like feature. And we are kind of changing the direction of the current. It can be straight and it can be like bending also. So this is completely driven by two light pulses or the laser pulses. So it will have probably potentially many applications in future, like in any circuit to give some sort of security. We can use this kind of technique. So just expose a light, current start flowing, it will act like a switch, an extra security feature to the integrated circuit. Other than that, we also excited different type of current distribution such that it excite a specially structured magnetic field. So here this all the bottom figure, these are the experimentally measured current distribution, and the bottom picture is just a calculated magnetic field using Biot law. Here first we excited a ring current distribution, that's why there is a magnetic field at the center. And using this technique, not only single ring, we also excited a lattice of ring current. And advantage is that at each lattice side sorry, each lattice side we can control the current circulation direction, like can be clockwise or anti-clockwise. For this case, we excite 3x3 lattice, total 9 sites where we can control the circulation direction of the current, and each current has a clockwise circulation direction. That's why the excited magnetic field you can see it as same direction. That's why same sign. And for the third case, here what we did, at each adjacent lattice site, the current circulation direction actually changed. If one is clockwise, another is anti-clockwise. So that's why if you see the excited magnetic field is changing sign, one is red, another is blue. That means if one is into the plane, another is out of the plane. So this is just like a sinusoidal magnetic field. And we can, using this technique, we can generate any kind of general current distribution. These are the few feature, few demonstration I have just shown. This kind of magnetic field is very, very interesting. So in potentially in a chip, we can generate such magnetic field, and we can use this to control the charge particle, because charge particle is sensitive to the magnetic field. Let's say in future, using this magnetic field, we can probably use this to generate a chip scale free electron laser kind of thing, because these are just like undulator magnetic field. Other than that, we wanted to show that we can control and measure current at a smaller dimension. This gives us opportunity to control many current element and high density current element. For that, we fabricated a 4 micron detector instead of 25 micron, and we just showed we can excite a 2+2 lattice. And if you see here, so this was 100 microns, overall current was excited 500 micron scale were, but here this scale bar is only 20 microns. So the overall the current was excited within 100 micron area, or 100 by 100 micron area. And other than that, we also excite some bow tie type of antenna structure using this method. But still now what we have, what I have explained to you, these are all specially resolved current, but there is no description of the time. But this current is generated by very, very short light pulses, femtosecond, very, very tiny, like in terms of time, very. But what about the time of this current that is generated by such transient laser pulse? What about the dynamics of such current? Obviously, this current is also very, very transient in nature. So once excited, the rise time will be very, very fast of such current, of the order of tens of femtosecond, depends on the pulse duration what we are using. And then after reaching a maximum, this current will try to decay very, very fast. And this will mainly depend on the material we are applying, and also number of density that is generated by these light pulses. as these are very rapidly oscillating current pulse, according to electromagnetism or electrodynamics, this will radiate uh, uh, some electromagnetic radiation. And for this case, as the overall current dynamics is below a picosecond, the electromagnetic radiation will be in the terahertz frequency range. So basically, this current acts as a source of terahertz electromagnetic radiation. Now, to measure such electromagnetic radiation, because terahertz, we can't see the terahertz. It's in between microwave and infrared. It's very, very difficult to like see or align such beam, but we use electro-optic sampling to characterize such radiation. So this setup I already shown you. The right side is the interferometer generating two color pulse, and then the gallium arsenide is there, that is focused there, and terahertz is generated, and we use another laser beam, we call it probe beam, to characterize such pulses, and we use electro-optic sampling. So here what we do, and we use a zinc telluride crystal, and there the probe beam and terahertz both are focused at the far field, and we just measure as a function of the time delay between probe and terahertz. What we measure, we just measure the ellipticity that is induced due to this terahertz. So this is the main principle of this electro-optic sampling. By this, we can like find the what is the time structure of this terahertz waveform, and this is just one example of terahertz pulse that is generated. This is in time domain. You can see this is the terahertz, and if we just take a Fourier transform, this is the frequency domain structure. And if we just change the relative phase, this is also like sinusoidally excite, and this confirm that this is coming from this two color current generation process. Now we have, I have seen that we can excite many such small current distribution. Each current like element that act as a source of terahertz. Now if we have many such current distribution, this can excite a structured terahertz. So all of you probably heard about this metamaterial or metasurface. So this is nothing but this is not a conventional metasurface, but this is a current metasurface, and we can actively control this metasurface to excite different type of structured terahertz light mode. And why structuring is so important in terahertz? Because structured terahertz has many applications in communications or imaging and spectroscopy and light matter interactions. But the main challenge is that as because current structuring or structural light is quite new field, and also in this terahertz frequency range there is very less like amount of research is done, and also the beam shaping element that is used to structure such light, that is not like available or rarely available. And also if some element available, that because of the dispersion is very like challenging to like control the entire bandwidth of the terahertz, because terahertz is a really broad bandwidth electromagnetic radiation. But in our case, our solution is that using these two color pulses, you don't need any extra shaping element, because shaping is already integrated into the source, and that's why it is free from any dispersion issue, and we can actively manipulate the current structure. That's why it will also change the terahertz electromagnetic radiation that is generated from that also. So following this same approach, recently we showed that we can excite a very interesting like a terahertz light mode in the terahertz frequency. We call it a flying donut mode. So you can see when we apply these two azimuthally polarized light, this generate a ring current density on the surface of gallium arsenide, and it's excite a terahertz mode, looks like a toroid. Here the electric field is along the body and magnetic field is just wrapped around that. And that's why at the center, if you see the magnetic field, this is almost spatially isolated from the electric field. So generally in electromagnetic wave, there is electric field, magnetic field. In conventional Gaussian beam, linearly polarized light, but they are always spatially coupled. But for this case, at the center, magnetic field is spatially like isolated from electric field. That's why it is very interesting to use such pulses in some pump probe experiment where we want to see only the effect of magnetic field. So first what we did, we just use some the theoretical calculations to show or to confirm by ourselves that this kind of ring current density that really generates such flying donut or flying torus or toroidal current terahertz mode. So this is purely theoretical calculations. So this is the electric field and space-time structure. This is the magnetic field space-time structure, and if we just take a first Fourier transform, this is the frequency, and it shows that such ring current density clearly generate a flying neuron mode. And by this calculation, we are motivated. We wanted to experimentally demonstrate or see and measure such terahertz mode. So this is the same setup. The right side, this is a interferometric setup generating two color pulse that is focused in gallium arsenide, and this is the same electro-optic sampling. But here, what we did specially resolved electro-optic sampling to measure spatially and temporally such current mode. This was the first scan here. So this shows the X component of the terahertz mode, and this is the Y component. And this is clearly shows this is a toroidal mode that is excited from ring current, because if you just see that toroidal mode, this looks like this, and this X component, this Y component, if you just plot together, then you can see this is just like a ring. And this is the space-time structure. So what we did, if this is the toroidal mode, we just take a slice of this toroidal mode along the diameter, and here the x-axis is the time or the probe delay, and y-axis is the radial coordinate. And for a given time, if we just go along the radial coordinate, you can see that along the zero, the field amplitude is minimum, and after zero, the field phase is actually flipped by 180 degree. And this is just a slice, and this is just transverse component. So this clearly shows that the excited pulse is a toroidal mode or the donut mode. So at the center there is a hole, and this just like a ring in 3D. Now we wanted to see what will be the effect of the current mode that we excite. So this is with the linearly polarized pulse, this is azimuthally polarized, and this is radially polarized. And for radially and azimuthally polarized, both excite toroidal shape pulse at the center. There is a phase singularity or electric field singularity. Now experimentally we measure the electric field space-time structure. So this is measured left side, and using Maxwell equation we calculated what will be the magnetic field corresponding to this flying donut or the toroidal mode. So this is the space-time structure of this magnetic field, this axial component. You can see at the center there is a strong component of the magnetic field, and for our case we achieved up to few millitesla from gallium arsenide using this technique, few millitesla axial magnetic field. But in terms of time, this is only close to a picosecond, very short ultra-fast magnetic field pulse. And very recently, this is all about current generation in semiconductor, like gallium arsenide. We wanted to study some low dimensional material. That's why first we used a monolayer graphene, where we generated such current. We applied two color pulse, and we generated and measured the terahertz field. So here, when we are changing the phase difference between two pulse by pi, then you can see the field is flipped. And this shows us this is coming from the two color process. We also wanted to compare the terahertz field that is coming from graphene and gallium arsenide, and this is just a monolayer single graphene. Though from this scaling we can see the amount of terahertz that is generated from gallium arsenide, that is much higher. But we have to remember that graphene just a single monolayer. That means that in terms of thickness, that is only below a nanometer, like it's close to 0.3 nanometer. And for gallium arsenide, it's a bulk material. So if we just compare the field per unit thickness or the per unit length, then the graphene is generating very efficiently the terahertz field using this method. And very recently what we did, instead of monolayer graphene, we stacked many monolayer graphene, and each layer that is separated by a 60 nanometer spacing layer by aluminum oxide. There we see that it's possible to generate high amount of terahertz variation using this method. And here the each graphene layer still acting like the 2D. Otherwise, like if you stacked many layers, that become like more like 3D material, like or graphite. But for this case, as this is separated by two, these are all decoupled. So each are 2D material, and they are just coherently adding the terahertz field from each layer. And we can see from this that after 50 layer, the terahertz field actually saturate, and this is mainly coming from our calculation. We can see this is coming because of the absorption of the terahertz and the pump beam by each graphene layer, because each graphene layer will absorb some amount of radiation that gives rise to this saturation after 50 or 55 graphene layer. So I'll now summarize my talk. But to explain that, I just told using the two color pulses, a beam of omega angular frequency and a little bit of that second harmonic of that 2 omega, we can control the current that we generate in material. And this current is very, very fast current and act as a source of very fast magnetic field. And not only just current, what we also experimentally did, we used structural light pulses using LCD like optical element, and using that we can excite any kind of current distribution. We call it the reconfigurable current pattern, and that gives rise to specially tailored magnetic field pulses. And also we demonstrate that the same technique can be used to excite different kind of terahertz radiation mode. And for our case, we are really interested to excite a toroidal light mode. We showed that we can excite a flying donut toroidal terahertz pulse. So we excited and characterized such pulses. And at the end, to optimize our experiment and the result, what we recently started exploring the low dimensional material. So we used graphene as a representative 2D material where scattering is limited. And we also use some multi-layer decoupled graphene. There we can see the amount of terahertz radiation that is kind of increasing with the number of graphene layers. And I'd like to acknowledge my group, my supervisor, Professor Paul Korkam, and my colleagues who are involved in this project, and our collaborator from different university and different lab who have helped during this project. Okay, then I'd like to thank you for your attention. Thank you very much. You can ask me if you have any questions.
Oh, hello. Hello. Thank you, sir.
Yeah.
Thank you, sir. We are grateful for your lecture. But sir, one or two questions. Basically, what I see here in your every slide, these are very frontline research. Okay, you are measuring up to 500 microtesla of magnetic field. So this is you need much more precious, I think, instrument. So whatever. But in your one slide, just to tell the coherent current control. So if you just simply say something about it, then it will be better for us to understand coherent current control.
So yeah, why we call it coherent current control? Because we are using very like short laser pulses or light pulses, and we are using the coherent property. Here the coherent means the phase of the light, specifically the relative phase between the two pulses. So that's why we call the coherent control or phase control current. So that's why this process is called coherence control or coherent control.
Acha. Thank you, sir. So we are extremely grateful for giving us so much time from your precious schedule. So thank you, sir. Thank you, sir.
Okay, thank you for inviting me also. Thank you. Have a good day.
Okay. Thank you, sir. Thank you, sir.
बहुत बहुत धन्यवाद सर। और ये हमारा सौभाग्य है कि आज यूएसए से सर जुड़े हुए थे और यूएसए से जुड़े हुए और इस ग्रामीण सुदूर कॉलेज में व्याख्यान उनका हो रहा है, तो इसके लिए अपनी नींद खराब करके, क्योंकि वहाँ अभी रात होगी, सुबह सुबह होगी और वो सोने वाले समय में प्रेजेंटेशन हम लोगों का दिए, वो उनके लिए बहुत बहुत धन्यवाद। तो इसके साथ ही मैं नेक्स्ट स्पीकर हमारे आनंद मोहन सर, जो कि बीडीओ हैं भगवानपुर के, वो हमारे समक्ष हैं। उन्होंने अपनी एमएससी की डिग्री बायोटेक में की थी, पीएचडी फ्रॉम मगध यूनिवर्सिटी बोधगया एंड रिसर्च स्कॉलर, और बीपीएससी 53 to 55 बैच के वो रहे हैं। तो बीडीओ सर से अनुरोध है कि वो मंच पर आकर अपनी प्रस्तुति दें। बहुत बहुत गौरवान्वित महसूस कर रहे हैं हम लोग कि हमारे बीडीओ सर एज ए रिसर्च स्कॉलर आज प्रेजेंट कर रहे हैं इस इंटरनेशनल सेमिनार में। बहुत धन्यवाद सर, बहुत स्वागत है आपका। जी जी, मगध यूनिवर्सिटी के विद्यार्थी भी रहे हैं। जी 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 सर।
से है मेरा
आनंद मोहन सर, श्री आनंद मोहन।
I am very happy to present here to represent my research paper related to water hyacinth. I think हम हिंदी में ही ज़्यादा बोलना कंफर्टेबल रहेंगे आप लोग के लिए। जो जलकुंभी होता है वाटर हाइसिंथ, वो काफ़ी ही अभिशाप है, खास करके इसको सौरो ऑफ वेस्ट बंगाल बोलते हैं। और इन आवर बिहार स्पेशली इन वैशाली डिस्ट्रिक्ट देयर इज सो मच सौरो ऑफ वाटर हाइसिंथ विथ माय ब्लॉक एरिया टू। सो इस पे सोचते हुए उस समय यशपाल मीना सर डीएम साहब थे, लगभग 1.5 साल पहले की बात बता रहे हैं। तो डीएम सर से हम डिस्कस किए थे कि सर वाटर हाइसिंथ पे हम कुछ काम करना चाहते हैं, सर आपका सहयोग चाहिए। तो जितने भी डिस्ट्रिक्ट हैं, हर एक डिस्ट्रिक्ट में जिला में रूरल सेल्फ एम्प्लॉयमेंट ट्रेनिंग इंस्टीट्यूट है, आरसेट्टी जिसको बोलते हैं। तो हाजीपुर में भी आरसेट्टी इंस्टीट्यूट है। हमने उनसे रिक्वेस्ट किया डिस्ट्रिक्ट एडमिनिस्ट्रेशन की ओर से कि वाटर हाइसिंथ पे हम लोग कैसे काम कर सकते हैं, कृपया आप इसमें हमें सहयोग करें। तो उन्होंने अपने ट्रेनिंग मॉड्यूल में वाटर हाइसिंथ के ट्रेनिंग देने के लिए नॉर्थ ईस्ट से प्रशिक्षक बुलाए थे, ट्रेनर बुलाए थे। और आगे हम आपको दिखलाएंगे, उसमें उनके द्वारा ट्रेनिंग दिया गया। और खास करके भगवानपुर ब्लॉक जो काफ़ी ग्रामीण क्षेत्र है, और यहाँ की जो स्टूडेंट्स हैं, जो महिलाएं हैं, रोजगार के लिए प्रयासरत हैं, तो उनके लिए एक बेहतर प्लेटफॉर्म साबित हुआ है। और लगभग अभी 100 के आसपास लोग इससे जुड़े हुए हैं। और हमें बोलते हुए बेहद खुशी हो रही है कि इस कॉलेज से भी बच्चे जुड़े हुए हैं इस काम में, वाटर हाइसिंथ वाले काम में। और आपके यहाँ पिछले साल हम लोग आए थे, तो उस मॉड्यूल में भी यहाँ पे जो बीएड का आपका सेक्शन है, वहाँ पे भी इसका हुआ था, डेमोन्स्ट्रेशन हम लोग किए थे। तो इसमें बेसिकली था कि किस तरह से इसको हम लोग दूर करें। देयर इज अ वाया रिवर इन माय ब्लॉक एरिया। वाया रिवर लगभग 80 to 20 किलोमीटर के आसपास स्ट्रेच है रिवर का इन माय ब्लॉक एरिया। सो पूरा वाया रिवर जो है वाटर हाइसिंथ से पटा रहता है। तो इसको मैनुअली जो फिशरमैन है, खास करके उन लोगों का मीटिंग हम लोग किए थे, और उन लोग के माध्यम से वाटर हाइसिंथ को पानी से निकलवाएं। और उसका जो जड़ होता है, उसका जो रूट और लीफ है, उस पार्ट को हम लोग सेपरेट किए। और स्पेशली जो स्टेम पार्ट है उसको ड्राई करना हुआ, और ड्रायर से हम लोग उसको सनलाइट में फुल्ली ड्राई कराए हैं, ताकि उसका फिजिकल स्ट्रेंथ है जो बढ़ जाए। और बढ़ने के बाद आप देख पा रहे होंगे जो ऊपर में बांस पे हम लोग बैम्बू पे रख करके इसको ड्राई कराते हैं। खासकर हमारा पंचायत सरकार भवन या पंचायत भवन गवर्नमेंट बिल्डिंग है, वहाँ पे स्वच्छता कर्मी लोग काम करते हैं, जो प्रतिदिन सॉलिड एंड लिक्विड वेस्ट मैनेजमेंट पे हर एक वार्ड में जाके डोर टू डोर कलेक्शन करते हैं। तो उन्हीं लोगों को हम लोग इसमें लगाए हैं, ताकि उनको सेल्फ एम्प्लॉयमेंट और एक्स्ट्रा मॉनेटरी बेनिफिट उनको मिल पाए। और इस तरह से जो हमारा वेस्ट प्रोसेसिंग यूनिट है, देयर आर 21 पंचायत इन माय ब्लॉक एरिया। तो एवरी पंचायत में हम लोग इसका जो रूट और लीफ है उससे मैन्योर प्रोड्यूस कर रहे हैं, मैन्योर बना रहे हैं, और वो बिक्री भी हो रहा है, जिसको हम लोग सरस मेला में भी एग्जीबिशन किए हैं पटना में, जिसको नेशनल लेवल पे भी मिला है। उसका एक वीडियो भी है, हम आपसे लास्ट में शेयर करेंगे। और ड्राई होने के बाद स्टार्टिंग में ही एक आप ये फ्लैटर मशीन है। ये फ्लैटर मशीन जो है, इसमें सिंपल ड्राई होने के बाद इसके स्टेम को जब हम लोग रोल करते हैं तो वो फ्लैट हो जाता है। उसके बाद इसका जो स्ट्रेंथ है वो बढ़ जाता है, एम्पावर हो जाता है, और नॉर्मल फोर्स से ये नहीं टूट सकता है स्टेम जो इसका है। और जितने भी थर्मोकोल, जो भी जूट पे या जिस पे भी काम होता है स्वरोजगार का, सेल्फ एम्प्लॉयमेंट का, तो उन लोग जो है एक थर्मोकोल का कोई भी पदार्थ बनाने के लिए, सब्सटेंस बनाने के लिए थर्मोकोल का डाया बनाते हैं, और उस डाया के ऊपर उसकी बिनाई होती है। उसी तरह से वाटर हाइसिंथ है, इसका हम लोग रूट और स्टेम हटा दिए, उससे बायो मैन्योर बन गया हमारा, उसका प्रोडक्शन भी हो रहा है, सेल भी हो रहा है मेरे ब्लॉक एरिया में, हम आपको आगे दिखलाएंगे। और उसका जो ड्राई स्टेम है उसको फ्लैटर मशीन से फ्लैट करके उसको डाया पे लगाकर सिंपल पिन्हाई का काम है, जिससे डिफरेंट टाइप का मटेरियल बन रहा है। इसमें आप देख सकते हैं ऑनरेबल सीएम साहब जो है श्री नीतीश कुमार सर, वो पिछले साल आए थे, हम लोग उनको हैट भी एक जलकुंभी से बना हुआ, वाटर हाइसिन से बना हुआ एक कैप सर को हम लोग डिस्ट्रिक्ट एडमिनिस्ट्रेशन की ओर से दिए थे। आगे आप देख पाएंगे जो टेबल पर जितना भी इस देख रहे हैं, इससे कोई भी चीज बना सकते हैं हम लोग। डोरमेट बन रहा है, टेबल मैट बन रहा है, पेन स्टैंड बन रहा है, डिफरेंट टाइप का जो आइटम है, और ये बायोडिग्रेडेबल है। सबसे बड़ी बात है कि ये पॉल्यूशन नहीं करता और इसको इजीली हम लोग डिग्रेड कर सकते हैं। इजीली इसको जो है आगे पीछे हो रहा है क्या? नहीं सर, ठीक है। तो आर सेट्टी के बारे में आपको बता रहे थे, रूरल सेल्फ एम्प्लॉयमेंट ट्रेनिंग इंस्टीट्यूट पूरा नाम है इसका, जो हर एक डिस्ट्रिक्ट में होता है। ये भारत सरकार की संस्था है जिसमें स्टेट गवर्नमेंट का भी शेयर होता है। इसके जो डायरेक्टर होते हैं, जो जिस डिस्ट्रिक्ट के लीड बैंक होता है, उसके मैनेजर जो होते हैं वो इसके डायरेक्टर होते हैं, और चेयरमैन डिस्ट्रिक्ट मजिस्ट्रेट होते हैं। तो यही आर सेट्टी के माध्यम से हम लोग ट्रेनिंग कराए थे, और ऑनरेबल सीएम सर के विजिट में भी हम लोग को इसको देने का उनको मौका मिला था। सीएम सर वाला दिख रहा है ना? ये यही दिख रहा है ना? ये दिख रहा होगा। अच्छा, हाँ। तो ऑनरेबल सीएम सर को भी हम लोग इसको सर को दिए थे। ये जो है सरस मेला 25 पिछले साल जो लगा था गांधी मैदान में, वहाँ भी रूरल डेवलपमेंट डिपार्टमेंट की ओर से काफ़ी वीडियो वायरल हुआ था गवर्नमेंट की ओर से, और काफ़ी लोग इसको पसंद किए थे। आप देख सकते हैं कि इसके टेबल पे जो स्टेम, ड्राई स्टेम है वो भी रखा हुआ है, और किस तरह का हम लोग मटेरियल बना पा रहे हैं वो भी रखा हुआ है। अभी हाल ही में समृद्धि यात्रा हुआ था सीएम साहब का अपने वैशाली डिस्ट्रिक्ट में, उसमें भी पहला स्टॉल ग्रामीण विकास विभाग का इसी का था कि समृद्ध गांव क्या किसे कहेंगे, और किस तरह से हम लोग बायोडिग्रेडेबल सब्सटेंस की डेवलपमेंट को ले जा सकते हैं। तो फर्स्ट स्टॉल जो था ग्रामीण विकास का था, और उसमें भी वाटर हाइसिंथ का हम लोग को एग्जीबिशन करने का मौका जिलाधिकारी महोदया के द्वारा दिया गया था। आप इसमें देख सकते हैं जिस दिन हम लोग ट्रेनिंग, ये वाला दिख रहा है ना, जिस दिन हम लोग ट्रेनिंग स्टार्ट किए थे, यहाँ के ऑनरेबल जो एमएलए सर हैं वो भी आए थे इनॉग्रेशन में, और जितनी भी स्टूडेंट्स और महिलाएं दिख रही हैं वो सब जो है ट्रेनिंग का पहला दिन का ये फोटो है। उनको ट्रेनिंग ब्लॉक के मीटिंग हॉल में दिया गया था, 1 मंथ का ट्रेनिंग था, और ये लोग काफ़ी बना करके इसको बिक्री कर रहे हैं। इवन डिस्ट्रिक्ट एडमिनिस्ट्रेशन या कोई हम लोग को गेस्ट आते हैं तो उनको देने के लिए हम लोग के पास उतना हम प्रोड्यूस नहीं कर पा रहे हैं जितना इसका डिमांड है। यही नहीं, अभी हाल ही में बिहार इलेक्शन असेंबली हुआ था 2025, उसमें इलेक्शन कमीशन ऑफ इंडोनेशिया के हेड आए हुए थे, उनको भी हम लोग रिप्रेजेंट किए थे डिस्ट्रिक्ट एडमिनिस्ट्रेशन की ओर से। और इलेक्शन कमीशन ऑफ इंडोनेशिया के जो चीफ आए थे, हेड आए थे, वो भगवानपुर का ही बूथ का विजिट किए थे। ये उसी मॉडल बूथ का है लेफ्ट साइड में, और राइट साइड में डिस्ट्रिक्ट मजिस्ट्रेट जो श्रीमती वर्षा सिंह मैम है, उनको हम लोग महादलित टोला में एसआईआर का जो काम हो रहा था, स्पेशल इंटेंसिव रिवीजन वोटर लिस्ट का जो हो रहा था एसआईआर का काम, उसमें महादलित टोला में हम लोग रात्रि चौपाल किए थे। उस समय इनको ये हम लोग सप्रेम भेंट किए थे। एक वीडियो होगा, चला दीजिएगा। कुछ पूछना चाह रहे हैं क्या? अच्छा अच्छा
सर, वो है नहीं आएंगे। अच्छा,
एक वीडियो होगा, वो चला दीजिए।
उसी में से,
उसी में है, नहीं तो फिर फोल्डर के पास ये वाला देखिए, चला गया
वीडियो सर।
हाँ, ये वीडियो है। इससे संबंधित एक वीडियो है जो बिहार सरकार के द्वारा आईपीआरडी जो सीएम हाउस से आए थे इसका वीडियो फुट करने के लिए, उसका वीडियो है जो हम आपको दिखलाना चाहते हैं। प्ले करेगा जलकुंभी बना, जलकुंभी करिए ना पहले। साउंड है ना?
जलकुंभी अभिशाप नहीं,
जो कभी एक बड़ी समस्या मानी जाती थी, आज वही जलकुंभी वैशाली में कला और आजीविका का नया माध्यम बन चुकी है। यह सिर्फ सुंदरता की कहानी नहीं है, बल्कि उपयोगिता, पर्यावरण संरक्षण और रोजगार के संगम की कहानी है।
कि जलकुंभी जो है वो एक तरह का अभिशाप है और खासकर नॉर्थ ईस्ट या अदर जगह पे इस पे काफ़ी खूबसूरत काम होता है और महिलाओं को रोजगार दिया जा सकता है, न्यू जनरेशन को दिया जा सकता है। तो रूट से संस्थान से हम लोग अनुरोध किए कि चूँकि बच्चियां और महिलाओं को यहाँ से जाने में आने में थोड़ा दिक्कत हो सकती है, तो कृपया प्रखंड सभागार में ही ट्रेनिंग दें। तो 1 महीने का प्रशिक्षण उनका चला है प्रखंड भगवानपुर में ही, और प्रशिक्षण के बाद वो लोग काफ़ी ऑर्नामेंटल सब्सटेंस इको फ्रेंडली सस्टेनेबल है उसको बनाते हैं। और कई जगह पे हम लोग सरस मेला है, हाट है और डिफरेंट जगह पे माननीय मुख्यमंत्री जी के भी आगमन पे हम लोग स्टॉल लगा चुके हैं।
जलकुंभी से बने ये उत्पाद प्लास्टिक का पर्यावरण अनुकूल विकल्प है। ये न सिर्फ देखने में आकर्षक है, बल्कि मजबूत, टिकाऊ और रोजमर्रा के इस्तेमाल के लिए बेहद उपयोगी भी है।
इसका जो प्रोडक्ट है मार्केट में इसका बहुत अब डिमांड हो रहा है। हम लोग ये प्रोडक्ट को मेला में भी सेल किए थे, वो लोग को भी ज़्यादा पसंद आया है। इसे हम लोग आगे बढ़ा सकते हैं और अच्छा बना सकते हैं।
वैशाली जलकुंभी कला स्थानीय स्रोतों से रोजगार सृजन के प्रयासों का परिणाम है। स्थानीय प्रशासन ने रूटसेट के सहयोग से 30 लोगों को प्रशिक्षण दिया। यह कला अब हरिवंशपुर, बंथू, हुसैना खुर्द, मियां बैरो, मंगनपुर और जहांगीरपुर पटेरा जैसे गांवों में तेजी से फैल रही है। तालाब में तैरती जलकुंभी से कलात्मक वस्तुओं तक का सफर आसान नहीं है। पहले जलकुंभी को पानी से निकाला जाता है, फिर उसके तनों को काटकर अच्छी तरह सुखाया जाता है। सुखाने के बाद जलकुंभी के तनों से तरह तरह की कलात्मक और उपयोगी वस्तुएं बनाई जाती हैं। पॉलिश और पैकिंग के बाद ये उत्पाद बाजार के लिए तैयार हो जाते हैं।
जलकुंभी है उसको निकाल के जड़ फुनगी काट के बीच वाले को सुखाते हैं। वो पहले हम लोग समझते थे कि वो कचरा है, लेकिन उस कचरा को अब हम लोग कंचन बना दिए।
जलकुंभी कला धीरे धीरे लोकप्रिय हो रही है। लोग इन उत्पादों को पसंद कर रहे हैं और बाजार भी लगातार बढ़ रहा है।
जलकुंभी को एक तरह से कहा जाए कि वेस्ट न समझ करके उसको हम रोजगार सृजन और वेल्थ के रूप में कन्वर्जन के लिए एक प्रयास हमारे भगवानपुर ब्लॉक में प्रारंभ हुआ और फाइबर को यूज करके अनेक प्रकार के उपयोगी सामान जैसे पर्स, हैट, गुलदस्ते, ये बहुत सारे चीज इतने अच्छे अच्छे आइटम्स उन लोगों ने बनाने शुरू किए और उसमें अब तरह तरह का इनोवेशन भी शुरू हुआ।
कलाकार अब नए प्रयोगों में जुटे हैं। उनका कहना है कि भविष्य में जलकुंभी से साड़ी बनाने की दिशा में भी काम किया जाएगा।
जलकुंभी से जो कला की आकृतियां यहाँ पर बनाई जा रही हैं वो हम लोगों ने खुद भी वहाँ पर जाकर देखा कि कितनी महिलाएं इससे जुड़ी हुई है, कितने युवा इससे जुड़े हुए हैं और बहुत ही एनर्जेटिक वे में वो लोग कार्य कर रहे हैं, क्योंकि एक वेस्ट को हम लोग वेल्थ के रूप में कन्वर्ट कर रहे हैं। इसका जीता जागता यहाँ पे अनुभव हो रहा है और अब तो ये थोड़ा सा इकोनॉमिकली फिजिबल मॉडल भी बनता जा रहा है। इससे अभी कमाई भी शुरू होनी हो गई है। आवश्यकता है कि इसको मार्केट से हम लोग लिंक करें और ज़्यादा इसका प्रचार प्रसार हो और इस कला को हम लोग ट्रेनिंग के माध्यम से, इसके वीडियोस बना करके और विभिन्न माध्यम से हम लोग चाहेंगे कि पूरे बिहार में स्प्रेड हो और पूरे देश में स्प्रेड हो, ताकि ये जो वेस्ट टू वेल्थ का मॉडल है वो पूरे देश में हम लोग अच्छे से संचालित कर सकें।
जलकुंभी कला आज रोजगार के नए स्रोत के रूप में उभर रही है। यह एक ओर जल स्रोतों की सफाई से जुड़ी है तो दूसरी ओर ग्रामीण अर्थव्यवस्था को मजबूत कर रही है। जलकुंभी की उपलब्धता वाले सभी ग्रामीण क्षेत्रों के लिए यह मॉडल एक प्रेरणादायक और अनुकरणीय उदाहरण है।
इस तरह इस पे और आगे काम करने का संकल्प है जिला प्रशासन का। डीएम मैम के द्वारा मार्गदर्शन दिया गया है कि भविष्य में इसका फाइबर निकाल करके किस तरह से हम लोग कपड़े में इस्तेमाल कर सकते हैं, साड़ी बन सकता है, शर्ट बन सकता है, तो उस ओर भी अग्रसर है और ट्रेनिंग मॉड्यूल के लिए भारत सरकार को लिखा जा चुका है जिला प्रशासन की ओर से। तो उम्मीद करते हैं इसमें हम लोग आगे और बेहतर करेंगे। और आज इस मंच पे उपस्थित होने का जो हमें गौरव प्राप्त हुआ, हमारे साथ सर हैं जूलॉजी हेड मगध यूनिवर्सिटी के। सर का आशीर्वाद मिला है और सर ने बहुत अच्छा हमें सलाह दिया है कि इसका केमिकल प्रॉपर्टी पे भी आप काम करें। तो हम सर से अनुरोध करेंगे, सर के मार्गदर्शन में सर इसका केमिकल प्रॉपर्टी पे भी हम काम करना प्रारंभ करेंगे सर जल्द ही। और उस पर करेंगे। और जो हम लोग का इंटरनेशनल सेमिनार का वेस्ट टू वेल्थ है, मतलब किस तरह से हम लोग वेस्ट को वेल्थ में ले जा सकते हैं, तो पर्यावरण संरक्षण में एज ए अधिकारी हम आपसे अनुरोध करेंगे कि प्लांटेशन जो भी जहां है कुछ भी अगर कर सकते हैं तो निश्चित तौर पे किया जाए, ताकि ग्रीनी एरिया हमारे अर्थ का बढ़े और भविष्य में जो पॉल्यूशन सबसे बड़ा संकट हमारे सामने है उसको हम लोग मिटिगेट कर सकते हैं प्लांटेशन के ही जरिए। यदि समय है तो 2 मिनट का एक वीडियो है प्लांटेशन का, एक थोड़ा सा देख लीजिए। तो भगवानपुर में लगभग 150 स्कूल है, जिसमें प्राइमरी स्कूल, मिडिल स्कूल, हाई स्कूल और +2 है। कुछ यहाँ शिक्षक भी हमारे बैठे हुए हैं। तो हमारे प्रखंड ने एक प्रण लिया खुद से कि जितना भी विद्यालय के छात्र छात्राएं हैं, स्टूडेंट्स हैं और जितने टीचर्स हैं, सभी को फ्री में प्लांट डोनेट करेंगे विदाउट एनी गवर्नमेंट स्कीम। सेल्फ हम लोग जो है पौधा वितरण किए हैं और मैक्सिमम स्कूल में पौधा रोपण भी किए हैं और बच्चों को भी दिए हैं। उसका एक वीडियो है छोटा सा, हम चाहते हैं आपसे शेयर करना। इसका यही उद्देश्य है कि हम लोग जहां भी रहें अपने कर्तव्य स्थल पर निश्चित तौर पे कुछ न कुछ अपने देश के लिए, अपने पर्यावरण के लिए, अपने राज्य के लिए, अपने कॉलेज के लिए, अपने स्कूल के लिए, अपने प्रखंड के लिए करें। तो कृपया इस वीडियो को अच्छे से देखिएगा और निश्चित तौर पे बच्चों को प्रेरित करना है और खुद भी प्रेरित होना है कि किस तरह से प्लांटेशन में हमारा रोल हो सके। हाँ देंगे, मैम से टाइम ले लेंगे, नेक्स्ट वीक आ जाएंगे, कोई इशू नहीं है। वो हमारा सेल्फ रहता है, कोई गवर्नमेंट स्कीम से नहीं देते हैं। हम आएंगे, हमें खुशी होगा। मैम अगर उसका बना देंगे कि कौन कौन पेड़ चाहिए कॉलेज में, कम से कम आज के बाद हम ट्रांसफर भी हो जाएंगे तो पेड़ के रूप में तो जीवित रहेंगे कॉलेज में। बस यही हमारी इच्छा रहती है। नहीं हो रहा है प्रतीश, देखिए ना एक और होगा। एक सैनिटेशन पे ही है, सैनिटेशन पार्क का है कॉन्सेप्ट, जिसमें हम लोग सैनिटेशन में क्या क्या कर सकते हैं। प्लांटेशन नहीं चल रहा है, ठीक है
होंगे कामयाब, होंगे कामयाब, हम होंगे कामयाब, होंगे कामयाब, होंगे कामयाब, होंगे कामयाब, हम होंगे कामयाब एक दिन। ओ मन में है विश्वास, पूरा है विश्वास, हम होंगे कामयाब एक दिन। होंगे कामयाब, होंगे कामयाब, हम होंगे कामयाब एक दिन। हो मन में है विश्वास, पूरा है विश्वास, हम होंगे कामयाब एक दिन। होगी शांति चारों ओर, होगी शांति चारों ओर, होगी शांति चारों ओर एक दिन। हो मन में है विश्वास, पूरा है विश्वास, होगी शांति चारों ओर एक दिन। हम चलेंगे साथ साथ, डाल हाथों में हाथ, हम चलेंगे साथ साथ एक दिन। ओ मन में है विश्वास, पूरा है विश्वास, हम चलेंगे साथ साथ एक दिन। वन्दे 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 मन में है विश्वास पूरा है विश्वास हम होंगे कामयाब एक दिन।
लगभग 40,000 पौधा हम बांटे हैं अपने प्रखंड एरिया में, और जहां भी पोस्टेड रहेंगे प्रयास रहेगा कि हम लोग पर्यावरण के लिए कुछ करें। और आपसे भी अनुरोध है इस संबंध में निश्चित तौर पे जहां भी हम लोग हैं अपने पर्यावरण के लिए कुछ बेहतर करने का प्रयास करें। और मैडम से एक अनुरोध रहेगा, प्रिंसिपल मैम से, एक बगल में मैम जस्ट 1 किलोमीटर भी नहीं है, अभी राजकुमार सर को हम ले गए थे, प्लास्टिक वेस्ट मैनेजमेंट यूनिट बना है, बहुत अच्छा से संचालित है, और WPU है, वेस्ट प्रोसेसिंग यूनिट है, और खास करके सैनिटेशन पार्क पूरे बिहार में कहीं नहीं बना है, सिर्फ भगवानपुर में बना है, जिसका इनॉग्रेशन दिसंबर में DM मैम के द्वारा हुआ है। तो मेरा आपसे यह अनुरोध है कि जो भी बच्चे साइंस के हैं खासकर और पर्यावरण के प्रति जागरूक हैं या कुछ सीखना चाहते हैं, तो फ्री में, कोई शुल्क नहीं है मैम, बच्चे या शिक्षक आके वहाँ विजिट कर सकते हैं, अपना वैल्यूएबल कमेंट दे सकते हैं, उसको हम लोग और अच्छा करने का प्रयास करेंगे।
थैंक यू सर। जोरदार तालियां सर के लिए, बहुत सुंदर प्रेजेंटेशन सर।
सफाई हो रही थी, देखा था आपने? सफाई हो रही थी, देखा था?
This international conference is especially आवाज आ रही है? Especially for creating that sense of spirit in each and everybody, not from the faculties of science, not only from the faculties of arts, not from the faculties of commerce. Rather, हम लोगों को ज़मीन पे ये सोचने की ज़रूरत है कि इतने वेस्ट को हम लोग कैसे रिसाइकल करें, कैसे उसका हार्मलेस डिस्पोजल करें, और उसको मैनकाइंड के हेल्प में और एनवायरनमेंट के हित में बायो फ्रेंडली, इको फ्रेंडली जो एफर्ट्स है उसके रूप में कैसे हम इसको जन जागृति के रूप में इस इंटरनेशनल कॉन्फ्रेंस को हम लोग को लेना है। और हमें बहुत ज़्यादा फ़ख्र है और खुशी है कि हमारे वीडियो साहब आनंद मोहन जी, जो हमारे भगवान गुरु के वीडियो भी हैं, वो ये बहुत कार्य बहुत अच्छे से कर रहे हैं, और इन्होंने ये जन जागृति जो इस एरिया में करने की कोशिश की है, सैनिटरी पार्क बनाकर या इस तरह का एक्टिविटी हम लोग एक रिसाइकलिंग पार्क, बायो रिसाइकलिंग पार्क हम अपने कॉलेज में भी कर सकते हैं। लेकिन इसको हम लोग वेस्ट नाम नहीं देंगे, हम लोग वेस्ट टू वेल्थ पार्क नाम देंगे, है ना। तो इस तरह से यह सर का जो आइडियाज़ है, इसको सर को हम लोग वीडियो साहब को हमेशा बुला के उनसे आइडियाज़ लेते रहेंगे, और हमारे कॉलेज के पर्यावरण को इम्प्रूव करने में इनसे जो हेल्प होगा वो भी हम इनसे लेंगे, और हम इनको और अपने आइडियाज़ कंट्रीब्यूट भी करेंगे। बहुत बहुत धन्यवाद। इसी तरह का मेंटालिटी को हम लोगों को सबको जागृत करने के लिए ये कॉन्फ्रेंस है। तो मुझे लगता है कि वीडियो साहब इस डायरेक्शन में पहले से ही काम कर रहे हैं। हम लोग मिलकर 1 to 1 11 और 1 to 1 111 और 1 to 1 करके हम लोग पर्यावरण को थोड़े हद तक संरक्षित करने में हम लोग मदद करेंगे, और एक सस्टेनेबल डेवलपमेंट के रास्ते में एक माइलस्टोन क्रिएट करने की कोशिश करेंगे, और डेफिनेटली होगा। जैसे मैंने देखा कि मैं आए दिन सोची थी कि मैं कैसे कर पाऊंगी, ऐसा कॉलेज है, जंगल कॉलेज है, लेकिन आज ईश्वर की कृपा से, भगवान लक्ष्मी नारायण की कृपा से एक अच्छा सा आयोजन हो गया। तो अब मुझे मेरा आत्मविश्वास बढ़ रहा है कि मैं ऐसे सारे लोगों को जोड़कर इस महाविद्यालय को, इस एरिया के पब्लिक को और सारे लोगों को एक अच्छी नीति से और अच्छे गोल के लिए जोड़ने का जो प्रयास कर रही हूँ वो अवश्य ही सफल होगा। और वीडियो साहब और इन सब लोगों के, इस तरह के मेंटालिटी वाले लोगों का काफ़ी सहयोग मिलेगा। ऐसे ही मेरी और वीडियो साहब के उज्जवल भविष्य की में हमें बहुत कामना है। वो और उज्जवल भविष्य के इसी तरह के अच्छे अच्छे काम और करते रहें, सैनिटेशन पार्क, और उनसे हम समय समय पर जरूर महाविद्यालय के बच्चों के लिए मोटिवेशन का काम के लिए या फिर कॉलेज के पर्यावरण के काम के लिए इनसे मदद लेंगे। और वीडियो साहब को बहुत बहुत आभार। आप और इस तरह के इनोवेटिव आइडियाज़ डेवलप करते रहें और पर्यावरण संरक्षण और सस्टेनेबल डेवलपमेंट की तरफ काम करते रहें। आपको बहुत बहुत धन्यवाद। आपका पेपर और वर्क बहुत रियली बहुत इनोवेटिव है और बायो फ्रेंडली, इको फ्रेंडली है। धन्यवाद।
और ये जो प्रस्तुति अभी है वो हम लोग पर्यावरण संरक्षण में 3R का नाम लेते हैं। 3R मतलब रिड्यूस, रीयूज और रिसाइकिल। और उसको ये जो प्रेजेंटेशन है एक तरह से उस पर एकदम सटीक बैठता है। इसलिए अभी के जो वक्ता थे उनको बहुत बहुत धन्यवाद और बहुत बहुत भविष्य के लिए शुभकामनाएं।
बहुत धन्यवाद सर। और एज ए रिसर्च स्कॉलर आज सर ने अपना पेपर प्रेजेंट किया, बट उनके पद और गरिमा को सम्मान देना भी हमारा अधिकार है और हमारा कर्तव्य है। तो बीडीओ भगवानपुर वैशाली को आज सम्मानित करने के लिए हम अपने महाविद्यालय के ऑनरेबल प्रिंसिपल मैम से अनुरोध करेंगे कि वो बीडीओ सर का सम्मान करें और जोरदार तालियों के साथ करबद्ध ध्वनि होनी चाहिए कि जोरदार तालियां। एज ए रिसर्च स्कॉलर इन्होंने पेपर प्रेजेंट किया और पद की गरिमा को सम्मान है सर। बीडीओ सर का जोरदार तालियों के साथ स्वागत है, अभिनंदन है।
Yes, yes. So, Sunesh here.
Now introduce.
थैंक यू सर, थैंक यू वेरी मच। और इस कड़ी को आगे बढ़ाते हुए नेक्स्ट स्पीकर हमारे हैं, वो हैं डॉक्टर कृष्णकांत मंडल। एंड दिस इज़ अ ग्रेट प्लेजर, it is my great pleasure to introduce Dr. Krishnakant Mondal, a distinguished academician from Department of Physics at University of Delhi, one of the India's most prestigious universities. Dr. Mondal is actively engaged in teaching and research in the field of physics and has made valuable contributions through the scholarly publications and participation in national and international conferences. Dedication have significantly contributed to the advancement of scientific knowledge and higher education. We are honored to have Dr. Krishnakant Mondal with us today and look forward to learning from his valuable insight and experiences. Thank you, sir. Welcome, sir. We are waiting, sir.
Thank you for this wonderful discussion, and thank you the organizer, especially Dr. Pintu Bhattacharya, for inviting me and giving me this platform to share my recent work. And okay, so today I'll discuss our recent work on modeling of industrially important zinc oxide copper based catalysts which are used for carbon dioxide to fuel conversion. So just a minute. Okay, so this composite, zinc oxide copper composite, basically known as industrial catalyst for carbon dioxide mitigation, mainly carbon dioxide to methanol conversion. And before 2000, so this catalyst is used for maybe last 50, 60 years, but its actual working principle or how this catalyst works was not very much explored. Till 2018, nobody has done the modeling of this cluster to this system to understand how this composite works. But there are many experiments, so that motivates us to do this exercise, and I'll share what we have learned from this our work. So this is the outline. So first I will give you a brief introduction to this field, and then what are the possible paths for carbon dioxide to methanol conversion, and then I will introduce widely to the audience that what is industrial catalyst and how it works, and different models of this industrial catalyst, what we have investigated and we have found to be the prominent active centers, and how we can improve this catalyst, and that is mainly the important focus of my presentation, that how we can improve this catalyst so that we can enhance the current production of CO2 to methanol efficiency, production efficiency. And then I will also touch upon the periodic table, how we can model catalyst taking materials from the choosing materials from the periodic table, how you should choose materials, and then the role of d orbitals, what we learned from our studies. I'll share those details, and then using this model, we have created a real catalyst, and how they work, that I will also discuss through one reaction, which is hydrogen evolution reaction, and then I will conclude my talk. So carbon dioxide to fuel conversion, basically, as you know, the CO2 is a greenhouse gas, and it is very important for today's scenario to reduce the CO2 from the environment. And one way is to store it, this CO2, and there are many plants are coming out around the world to store this CO2 underground, and that is another way. And but there actually the main problem is to store the CO2 and spend money and reduce the CO2 from the environment. But if you want some cost-effective way so that you can remove the CO2 as well as you can get some money out of it. So for that reason, CO2 to fuel conversion is a very promising approach, and people are using for this approach for maybe last 50, 60 years, but it's not very efficient still now. So that's why this method or existing methods are not so popular. Although many industries are nowadays coming out with different approach to convert CO2 into fuel. And how these things can be done, the source of CO2, we can get it from any fossil fuel burning from the industries or from the air directly, or any biomass, you can get the CO2 and convert it into fuel. You need another feedstock, which is hydrogen. And the hydrogen basically are generated from electrolysis of water, which is a very well-known and cost-effective method. And this is the process which is also a rate, or which is also a limiting step for this entire process, how to get a cheaper hydrogen to make it more cost effective. So that part is also a lot of research is going on around the world to make this process also cost effective. And another step is that you mix these two gases, CO2 and hydrogen, and convert it into fuels like methanol, ethanol, and any other usable fuels based on carbon. Like sometimes people are synthesizing methane as well, ethane, methane, any gaseous compounds also. But in this process, CO2 to fuel conversion, in this process, you need a catalyst to accelerate this step. So both this hydrogen production and the CO2 to fuel conversion, this process need catalyst. And this is where the people who are working in the material science like us are important. So this is the two steps which people are working, and we need to focus on this more and more to make this process efficient. entire process efficient. And once you get this methanol, ethanol, you can directly use it for fuel in your car. Like nowadays, ethanol mixed petrol is very common scenario enter the country and enter the world as a whole. So this is going to be the future fuel for our cars or any mobility vehicles. And you can also generate power, like you can use it as a generator, you can use, and you can use it as a generation of power as well. And these are the current scenario I just highlighted, that how many people are, or how many publications are coming out, and you can see that it is drastically enhanced recently, and it is continuously growing, and this field is attracting more and more research, and people are publishing more and more to understand these processes and to make it more and more efficient. And recently, our Indian government also has a mission to make methanol or ethanol more, production of methanol, ethanol more and more. And our Indian industries like Assam Petrol Limited and NTPC or BHEL, all these big PSUs, they are actually coming out new ways to convert CO2 to fuel. And worldwide, this is a very huge market is there. As per report, it is $1.21 billion market in 2024, and they're expected to be more than 2 billion in 2035. So you see how this field is growing. So this is the path where CO2 becomes methanol, and this path, basically there are three well-known or well-reported, I will say, paths for CO2 to methanol conversion. And one is known as format path, and another one is RWGS or reverse water gas strip path, and another one trans-UOH path. Mostly format and RWGS, these two paths are well documented and well studied, because these are two paths are always found to be the more prominent paths for CO2 to methanol conversion. And this is what we notice when we do this exercise, is that the activation of CO2 at the initial state, how it's absorbed on the catalyst, that actually decides the selection of path. If the CO2 is activated at the beginning, like when it is absorbed on the catalyst, then it most likely will take the RWGS path. If the CO2 is not activated, like it absorbed linearly from the catalyst, which indicates that it is not absorbed, then it is kind of physi-absorbed, quickly absorbed on the catalyst, then it will take the format pathway. So this path I will explore more on context of our catalyst. And this is the industrial catalyst, as I mentioned at the beginning, that basically zinc oxide and copper mixture, which is supported on alumina surfaces, and this composite, copper zinc oxide composite, basically works as a catalyst or active center, and the gas mixture which is used is the syngas, CO2, carbon dioxide, and carbon monoxide, and hydrogen. And the temperature range which is reported is very high temperature. You can see the values 493 to 553 Kelvin, and pressure is also very high. These two steps are main rate limiting or the limiting processes, or which actually increase our cost. And also the efficiency or the conversion efficiency of CO2 is also very weak or very low in these industrial catalysts. but still this catalyst works, and I will discuss why. And then people have reported experimentally that Powell active configuration is reduced zinc oxide on copper surface or copper nanoparticle. There are many reports on that. And then also it is reported that zinc oxide may form a graffiti layer on the copper nanoparticles. So these are most widely experimental reports which says that these two are there. But there was no theoretical understanding how and what kind of structure it is, what exactly the reaction center, and who is important, zinc oxide, copper, or anything else, or what is the effect of hydrogen on this catalyst. All these things are not reported so far. So we did a theoretical investigation to understand this catalyst in detail. So we model this zinc oxide copper system because alumina is just a support, so we didn't take it for our computational to reduce the computational cost. So we just focus on the zinc oxide copper composition. And for copper also, we take the 111 surface, 111 surface, which is reported to be the most stable surface and widely reported in the literature that this is the surface what they found while they investigate in the zinc oxide copper system. So we choose different reduced zinc oxide cluster on copper surface to mimic the reduced zinc oxide system as reported in the experiment. And these are the different reduction processes we followed. Maybe it can reduce through carbon monoxide because carbon monoxide is also there in the system, or through hydrogen. Hydrogen is also there in the system. So these are the processes, and we calculate different free energy of the different systems on copper surface at different not different temperature, particularly at experimental conditions. And then we found that zinc oxide systems, in all the systems, zinc oxide comes out to be motif, which is zinc 3O, 3 zinc and 1 oxygen. That builds the entire system, like how big your catalyst, how big your cluster is, always you will get this zinc 3O motif. And that is why we actually concentrate more on this simplest model, because these are all model calculations. So we always try to get a smaller system so that we can explore more with less computational cost. And then we did so we investigate the full reaction on the zinc 3O copper system, and crucial steps what we found to be the more important, those steps we did on the other system. So this is the different path as I introduced in the beginning, and we also did it theoretically, and we found that in our case the CO2, the gas CO2 molecule weakly absorbed on the zinc 3O motif, and this is kind of Fiji absorption around 0.15 eV, which is nearly nothing at normal temperature. So this is very weak absorption of CO2 on this system, and that leads to the Fermat path, as I mentioned in the beginning. So Fermat path is found to be the more favorable, and the reaction barrier what we calculate is 1.3 eV for this to happen. And then we also investigate the rate limiting step on the other bigger systems, because as I said, bigger systems are difficult to handle. So the full reaction is done on this smallest motif, and the bigger and the limiting steps where CO2 to formation, that is the limiting step. That step we investigate in other systems as well. And we found that the barriers are more or less fixed, of the order of 1.2 to 1.3 eV. So whatever system you use, you will always get a same reaction barrier. And this is actually one advantage of this zinc oxide copper system, because the reaction barrier does not depend on the structure, and that is why it is known as industrial catalyst. Because in the industrial catalyst, you should not use a system which is very sophisticated or very sensitive to the structural property. The catalytic properties should not depend on the structure more, so that you can get any structure and you can easily use it for bulk production. And what we observe here is that the weak absorption of CO2 may be the main reason for high temperature and barrier, for high temperature and pressure for this reaction. So the low efficiency. To enhance this process, we have to actually enhance the CO2 absorption, and that is what I will show at the end. And then also water in this process, in the methanol synthesis, water is a byproduct. So the water will be there in the system. So how the water affects your catalyst, that is another question we need to understand. And then also we concentrate other systems like graphitic layer of zinc oxide on the copper system. So because that is also experimentally observed. So for that, we took different ribbon-like zinc oxide, graphitic zinc oxide, which is also reported in the theoretically as well as experimentally, that zinc oxide systems can form graphitic layer on metal surfaces. And as I said, zinc oxide on copper surface is already known. Graphitic layer of zinc oxide is already reported for this industrial catalyst as well. So we choose the graphitic layers in the form of ribbon and place it on the copper surface. And what we observe is that so not only the graphitic layer, we also take some bulk-like structure and a graphitic layer attached to it, which is here this step 1 and step 2 structure. Because there are some reports that zinc oxide can form tape-like structure, which is I have mentioned here on silver 111. So there are many possibilities we have considered. And then this is the energy diagram of all these systems, which actually shows that the graphitic layers are more stable when you place on them on the copper surface, and they are much more stabilized when you add hydrogen onto it. That means all the oxygen sites are hydrogenated, then these systems are more stable. An interesting point is here is that if you hydrogenated the all the ribbons like structure, as you can see in these systems, we call it like W2, W3, W4, depending on the number of chains of zinc oxide we use. Here 2 chains are used, so it is W2. Accordingly 3 and 4 like that. And here you can see that if you add more and more, if you add hydrogen on this system, then their energetics becomes similar for all the ribbons, although they were different on the copper surface as well as on the gas side. But on the hydrogenated case, all the ribbons are of the same energy. That means if you have W2 or W3 or W7, like bigger or even sheet is actually a continuous sheet of zinc oxide, which is supported on copper surface, all are of the same energy. This indicates that these systems basically are very fractional. Fractional means they can take any step, or this zinc oxide, hydrogenated zinc oxide can take any step. And once there is a fractionality in the system, then there is a possibility of structural structure reconstruction. What we observe in the next. So we also investigate the reconstruction of this ribbon-like structure under hydrogen. And also we found that for this reconstruction process, we need 2 more wedge groups. And these wedge groups, we believe that they can come from the water dissociation, because water is already there in this system, so they can dissociate and you can get OH group easily. So in presence of hydrogen and OH, you can have this reconstruction, and this reconstruction undergoes a very beautiful structure of zinc 6 O7H7 configuration, and this configuration actually attached uh, to the single chain which is remaining at the end, and it may be W2 or W3. So rest of the chain will remain intact, only the end chain will go for reconstruction, and once the reconstruction is there, then your structure is also more stable. That means this reconstruction is energetically favorable. There is a barrier to perform this reconstruction. This barrier basically is of the order of our actual reaction barrier for methanol synthesis. Because this barrier of 1 EV, which is of the order of our methanol synthesis barrier, can be easily overcome during the reaction. So this reconstruction can happen during the synthesis process. And the same time, there is another report which is published around 2017. We also actually did this work around that time. So they have published that this zinc 607H7, this cluster, they have reported as a model for their experimental validation. So our cluster and their model looks alike. That means this kind of reconstruction may have happened during this synthesis process. And then we investigate other structures, like as these people have reported that cluster-like structure can happen or can be found during the synthesis. So we also try to understand different zinc oxide cluster under hydrogen and OH, different hydrogen and OH concentration. So we did this investigation where we actually generate many zinc oxide, hydrogenated zinc oxide, and as well as hydroxylated zinc oxide cluster. And we took three or four different composition of oxygen and hydrogen, sorry, oxygen and zinc. So zinc 3O3, zinc 4O4, zinc 5O5, and zinc 6O6. This kind of clusters we have chosen and hydrogenated them as well as hydroxylated them, and try to find out the minimum energy configuration. And this process is very tedious process because you will have a lot of structures in the system, so you have to be very cautious to generate the structure. So we use a very well-known method which is known as Bashing hopping method, which is actually known as global optimization techniques, which actually helps to find out the global minima or minimum energy configuration for a particular composition. And this is a process we adopt, and then we generate around 40,000 structures of these four structures, and then we identify the most stable configuration. And we found, and one interesting point in this cluster is that when you have zinc oxide and OH ratio is 1:2, then your systems are very stable. And these systems are more stable because zinc hydroxide as a bulk is also available in the literature. That means you can synthesize zinc hydroxide as a bulk. So they resemble like a bulk composition, and that is the reason this zinc oxide, hydroxylated zinc oxide clusters are more stable with 1:2 ratio. And then we deposit this cluster on, so these are the properties of the clusters. I just keep them, and then we deposit these clusters on the copper surface and try to understand how they interact with the CO2. And we found that CO2 molecule interact very weakly on this system. And another point we observed is that if there is excess water in the system, then that actually hinders the adsorption process. That means the excess water in the system can damage your catalyst, which is also experimentally reported that water poisoning is a very common phenomenon in this entire process. So you have to remove the water efficiently from the system as well. what we also observe in our theoretical understanding. Now, what next? How we can improve this absorption of CO2 on this system? So this is what we try to find out. So we observed that one process, we took a very simple example of CO2 and try to activate it. If I put charge on CO2, then the CO2 bends and it gets activated because the bond length increase and bond angle changes. If you somehow put charge on CO2 in any means, you can get an activated CO2. Once the CO2 gets activated, you can actually go through for the hydrogenation process with a very less barrier. So look into the periodic table and found that oxygen is next to the nitrogen, which is less electronegative. So it can easily give away electrons, may give an electron to the CO2. And then I choose nitrogen as a replacement for oxygen. And then I also check for literature because this is a theoretical work. So whether experimentally people can synthesize these systems or not, I have to check. So I checked for the literature and found that yes, nitrogen dope zinc oxide is well documented and experimentally it is verified. And also experimentalists have observed that the nitrogen actually stays on the surface, which is good for me because CO2 can directly interact on the nitrogen and that charge transfer process can happen and my activation of CO2 can happen and also we can go easy reduction of CO2. So for that we model our system as we already had this zinc oxide system. So I took one system cluster. This is done on the cluster model and to understand the effect of nitrogen. So I replace one oxygen with nitrogen and create the reaction center, and the entire process remains same. Found is that in this system, nitrogenated system, CO2 at the beginning is very much activated, and the absorption energy is over 10 times higher than the actual zinc oxide system. That means I can enhance the absorption of CO2 as well as I can activate the CO2. Once the CO2 is activated, then actually the reaction process is different now. Now the reaction proceeds through the RWGS, which is reverse water plastic process, which is I also mentioned at the beginning. Now there is a common question that if there is a nitrogen, then there is a very easily it can go to amine formation. So we also form amine and try to understand if there is an amine, then whether CO2 can still interact and go for further hydrogenation or not. Yes, we did the same thing and we found that yes, with the amine formation also the CO2 interact with the nitrogen, but now the adsorption is slightly reduced, but still it's quite high as compared to the pure zinc oxide. This means I can increase the CO2 capture process and also the activation of CO2, which leads to the conversion of CO2 from CO2 to methanol in an easy way. But no, the process is not easy. Still, we found that the reaction barrier is of the order of 1. That means we cannot reduce the temperature requirement, which is the thermal energy to encounter the or to overcome the barrier. But we can reduce the pressure because that is important for the CO2 absorption. Now my CO2 is strongly absorbed, so I can reduce the pressure. That means this nitrogenated zinc oxide can work at low pressure, but temperature may remain high. Although this combination of temperature and pressure is not yet done, so we are in a process to understand the different temperature and process how affect this reaction. So this is then I would actually stop here because I have already crossed my time, I guess. So this is another work we propose for modeling cluster for this zinc oxide, for CO2 to fuel conversion. So these are the different systems, and this is our model, which is already published. So this is our model, and this is our actual system. based on our molecular model, and we believe these models are working, and we are actually in a process to give a database from the periodic table which can help the experimentalists to choose the elements for different reactions for hydrogen production or CO2 to methanol or methane or ethane conversion. And so we did this for our cluster, for our system for each year. And this is the conclusion I like from here. And okay, so what we learned from this study is that weak adsorption of CO2 on zinc oxide system, and that is the reason behind the low conversion of CO2 to methanol, and zinc oxide structures are more stable at hydroxylated condition, and hydrogenated zinc oxide systems are as good as zinc oxide system for CO2 mitigation, and this is the main reason that zinc oxide proper system is industrial catalyst, because whatever condition you apply, they remain same. That means they do not change their course of or they do not change the reaction process, or any intermediate may not get affected due to the condition of the structure, or what kind of structures you have, or what type of situation you have created, like over hydroxylated or not, it may not affect. But the water may poison the system, so which is also experimentally documented. And then we report that electron donating elements like nitrogen can enhance the CO2 capturing capability, and which may reduce, I can't say can because we have not done it properly, so which may reduce the requirement for high pressure. And then finally, we actually propose a new model where we observe that the partially filled d orbital metal are more useful for capturing CO2. And also, we have some models which propose a model which is, we call it as a bimetallic cluster. They can be used for real catalyst design and can help the experimentalists to choose efficient material for CO2 to fuel conversion. And I would like to acknowledge my PhD student who has just graduated and currently postdoc, and Saptarshi, and my collaborator who has supported during this study, and the computational facility from Spinetta, Italy, and CDEC Pune, and the funding from BST and the Institute of Eminence from Delhi University. And thank you for your attention.
Hello.
And I'd like to take questions.
Thank you, Vishnukanto sir. Applause to him. Okay. Sir, basically,
hello.
We are grateful to you for give us so much time from your tight schedule. Okay, your lecture is basically James for our session, and you basically discuss about CO2 fuels. Some things just we understand, something we may not, but your research shows very potent research, as I think. So, sir, once again, I am just acknowledging my gratitude to you. Okay, thank you, sir. Thank you. Okay.
Thank you.
Thank you, sir.
Thank you so much, sir, for this wonderful session. अब हमारे समक्ष हैं SDFC बैंक भगवानपुर के ब्रांच मैनेजर साहब से अनुरोध है कि वो मंच पर आए। श्री पंकज कुमार सिंह सर से अनुरोध है कि मंच पर आए, पधारें। जोरदार तालियों के साथ हम ब्रांच मैनेजर HDFC श्री पंकज सर का अभिनंदन करते हैं, स्वागत करते हैं। बहुत धन्यवाद सर आपका। आगे भी कॉर्पोरेट सोशल रिस्पॉन्सिबिलिटी के तहत सर आपसे आशा रहेगी। थैंक यू सर। माननीय मुख्य अतिथि, सम्मानित वक्ताओं और सभी प्रतिभागियों का हार्दिक हार्दिक अभिनंदन है। इस सेमिनार से हमें बहुत मूल्यवान ज्ञान प्राप्त हुए और हमारी सेशन की अध्यक्षता कर रही ऑनरेबल प्रिंसिपल मैम से अनुरोध है और उनकी आज्ञा से इस सेशन के समाप्ति की घोषणा की जाती है और कल इस समाप्ति की घोषणा मैम आज के तकनीकी सत्र के समापन की घोषणा मैडम की परमिशन से की जाती है और कल फिर हम इस 3 दिवसीय सेमिनार कंजर्वेशन ऑफ बायोडाइवर्सिटी मैनेजमेंट, रीसाइक्लिंग ऑफ वेस्ट, क्लाइमेट चेंज एंड सस्टेनेबल डेवलपमेंट के टॉपिक पर कल फिर हम कुछ नए वक्ताओं को कुछ नई बातें, कुछ नई ज्ञान अर्जित करेंगे। तो आप सबों का साथ देने के लिए बहुत बहुत धन्यवाद।